This video is on Born-Haber cycles. So our aims for this video are to construct Born-Haber cycles to calculate lattice enthalpies, compare lattice enthalpies to provide evidence for covalent character in ionic compounds, calculate enthalpies of a solution from lattice enthalpies and enthalpies of hydration, and calculate enthalpy changes using bond enthalpies and explain why these values may be less accurate. So the easiest way to go through Born-Haber cycles is to go through an example. And basically a Born-Haber cycle is like a complicated Hess law cycle. Much more complicated because there's far more steps. And it's not so much a different route more than a whole cycle. And when you'll get given an exam are different enthalpy changes. So here we've got the enthalpy of atomization of chlorine, which is the enthalpy change when 1 mole of chlorine atoms is formed from gaseous chlorine. Electron affinity of chlorine, so that's where you add 1 mole of electrons to chlorine atoms to make chloride ions. Enthalpy of atomization of silver, so that's to make gaseous silver atoms from silver solid. First ionization entropy of silver, so first ionization enthalpy of silver, sorry. That is when you remove a mole of electrons from silver, and enthalpy of formation of silver chloride is where you form silver chloride from its elements in their standard states. So we can write equations, or symbols at least, on these lines to show the different steps. So one of the first steps could be, in this case, your chlorine breaking apart to form chlorine atoms. So that would be the equivalent of your enthalpy of atomization of chlorine. So this is going to be Ag solid. You need to make sure you keep your state symbols in, plus Cl gas. Remember, it's from half Cl2, so you're going to make just 1 chlorine atom. And then you could turn your silver into a gas. So you're going to have Ag solid plus, Ag gas plus Cl gas. And that's also going to take energy, so we're going up the energy scale here, using energy each time we go up. And then we're going to, another step that would take energy is the enthalpy, first ionization enthalpy of the silver. So there you're going to form Ag plus, which is a gas, plus Cl, which is a gas. And then the electron affinity of chlorine is actually a negative enthalpy change. You can see that in the table, minus 364, and so that's this arrow here. And then we can calculate a value for the enthalpy of lattice association for silver chloride, which is this arrow here, dissociation going from silver chloride to the 2 ions, by putting numbers on these arrows and then going through the cycle. So this arrow here is your enthalpy of formation, going from silver and chlorine in their standard states to silver chloride. So that's going to be minus 127. This arrow here is the atomization of chlorine. So that's 121. Then we've got the next arrow, which is the atomization of silver. So that is plus 289. Then we've got the first ionization energy of silver, so that's 732. And then on this side we've got the electron affinity of chlorine, which is minus 364. And we're trying to work out this arrow here. So to work out this arrow here, we're going to go from this level up, 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 and back down again. So we're going to have to swap this arrow around and make this a positive instead. So this arrow is going to go around, going to have plus 127, then just add up all those numbers and that gives us our dissociation. So we've got 127 plus 121 plus 289 plus 732 minus 364, and that gives us plus 905. Now the common mistake with these cycles is getting these wrong way around, so going this way instead of this way. And the easiest thing to do there is just to check your number at the end to make sure it makes sense. So a lattice dissociation enthalpy going from AgCl to Ag plus and Cl minus, i.e. breaking apart the lattice, is going to take energy. And so it makes sense that it's an endothermic enthalpy change. And so the positive sign of this 905 makes sense. Now, before we can start to cover the aim here to compare lattice enthalpies to provide evidence for covalent character in ionic compounds, we need to understand what is meant by the term the perfect ionic model. So for ionic compounds, the perfect ionic model is where the two ions are point charges and that there's no polarization between them. So this is the positive ion and this is the negative ion, and there is no polarization, which means there's no covalent character. Now, for most ionic compounds, this actually isn't true, and the more polarizable the negatively charged ion is by the positively charged ion, the more covalent character you're going to get. So if you've got cesium and fluorine, for example, cesium fluoride, you're going to get an almost perfect ionic model because the cesium is pretty large and positive, and the fluoride is the smallest negative ion you can get. And so the fluoride ion is very difficult to polarize because it's very small, and because the cesium ion is positively charged ion is big, it's not going to do a great deal in order to polarize the negative charge. And as you go down the continuum, you get more polarization from eventually forming covalent compounds, which are compounds between two of the same atom, if you like. And you can see if there's covalent character within a compound, within an ionic compound, based on the comparison between an experimental lattice enthalpy and a theoretical lattice enthalpy, because the theoretical lattice enthalpy is based on the assumption that the perfect ionic model exists in the ionic compound. And so you can create a Born-Haber cycle based on the idea that the ionic compound has the perfect ionic model. Now, if that isn't true, then the experimental value of the lattice enthalpy would be much more different, or a lot different, to the theoretical value. So, we'll get to that in a second. First, explain the meaning of the term perfect ionic model. This is where the ions are point charges, so there is no polarization. Okay, and then the next question says, state what you can deduce about the bonding in NABR from the data in the table. So here, NABR, the theoretical lattice enthalpy, is very similar to the experimental lattice enthalpy. So you can say, or you can deduce, that this compound must be ionic. However, with the other one, AgBr, you can see that the experimental value is 890, but the theoretical value is 758. So the difference between those two values shows you there is some covalent character within that molecule. So you can say it's ionic, but with some covalent character, i.e. there is polarization occurring between the silver ion and the bromide ion. The next aim is to be able to calculate enthalpies of solution from lattice enthalpies and enthalpies of hydration. Now I'm going to again do this via an example. It says use this data to calculate a value for the enthalpy of solution for CaF2. Now when you're actually working out enthalpies of solutions, or you're using enthalpy of hydrations, you can just do a bog standard Hess law cycle in order to work this out. Because what we're trying to work out here is the CaF2 turning into Ca2 plus aqueous and 2F minus aqueous. Now actually the lattice formation for CaF2 is going from Ca as a gas, and 2 plus as a gas, and 2F minus as a gas to the CaF2. That is the lattice enthalpy. But also the enthalpy of hydration for Ca2 plus ions and F minus ions is going from the gaseous 2 plus ion to the aqueous 2 plus and the aqueous F minus ions. So we can just use this very simple Hess cycle. So this is the delta H we're trying to work out. This arrow, the first arrow, you can write on there the lattice formations. That's -2, 6, 1, 1. On this arrow, that's the hydration for Ca2 plus, so that's -1650. And this arrow is 2 times the hydration for F- ions. That's -506 times 2, so that's -1012. Then we're trying to get from here to here, so we're going to go down this and back up this side. So this arrow needs swapping around, so we're just going to switch that arrow around, make that positive, and then to work out delta H, we just add together these values. So we've got 2611, take away 1650, take away 1012. And that gives us an enthalpy of solution for calcium fluoride of -51 kilojoules per mole. So if you're working out enthalpies of solutions, then you can use this Hess cycle idea. If you're trying to work out lattice formation or formation enthalpies, then generally a Born-Haber cycle is more appropriate. So this final aim, be able to use bond enthalpies to do calculations and explain why these values may be less accurate, is really from Chem 2, but you still have to be able to do it for your Chem 5 exam. And again, I'm just going to use an example to go through in order to explain this. So it says ammonia can be manufactured by the Haber process. The equation for the reaction that occurs is shown below. The table below shows some bond enthalpy data, so there it is. So it says use data from the table to calculate a value for the enthalpy formation for 1 mole of ammonia. So here's your enthalpy change for the formation of ammonia, but for 1 mole of ammonia we need to divide all this by 2. So we're going to have N2, which is a triple bond N, and half of that, plus 3 halves H2, which is HH single bond, goes to make NH3, which is N with 3 H's attached. And then bond enthalpies, your arrows go down first, so we're going to go down, down, down. And in this first one, we're going to have half times 944. This second one, we're going to have 3 over 2 times 436, which is the HH bond enthalpy. And this last one, we've got 3 NHs, so it's 3 times 3, 8, 8. Just make sure we know all these numbers before we carry on. So half times 944 is 472. 436 times 3 over 2 is 654, and then 3 times 388 is 1164. Now we're trying to work out this arrow here, so we need to go down first, then back up again. So this last arrow needs swapping around, and we're going to turn this into a negative sign, and so your delta H equals 472 plus 654 minus 1164, and that equals minus 38. And then it says a more accurate value for the enthalpy of formation of ammonia is minus 46. Suggests why your answer to part 3A1 is different from this value, and that's because, as you learn in Chem 2, these values are averages taking over a range of compounds, and so are not specific to these bonds here in this formula. So bond enthalpies are averages taken over a range of compounds. So let's have a look at a few past exam questions. So in this one it says use the following data to calculate a value for the lattice association enthalpy of sodium chloride. So we're looking at a lattice association enthalpy. So we're going to use a Born-Haber cycle in this case. So if you just look at what we've got sodium, the atomization of sodium, we've got the first ionization energy of sodium, we've got the atomization of chlorine, although this is not quite the atomization energy of chlorine, enthalpy of chlorine. You've got to just be aware that this is Cl2 turning to 2Cl. Remember definition of the enthalpy of atomization of something is to make 1 mole of atoms. So just be aware of that when you're putting that into your cycle. You've got the first electron affinity of chlorine, and you've got the formation enthalpy of sodium chloride. So what you want is to go from sodium chloride, NaCl, to Na plus Cl minus. So we've got to think about how we're going to get around to that. So the first step we can do is we've got an equation that shows the formation of NaCl. So we've got Na plus half Cl2 going to that, and then we can then set about first atomization of chlorine. So you've got Na solid at the moment plus 2Cl gas. Then we'll atomize the sodium to make sodium gas plus 2Cl gas. Then we'll want to go up again to the first ionization energy of sodium. So you have Na plus 2Cl, and then we'll go from there to the Cl minus. So that's the first electron affinity. So we've just got to put our numbers on. So this isn't to scale, obviously. So you're going to have the formation enthalpy, which is minus 411 on the bottom. You've then got the atomization of chlorine, which is 242. You've got the atomization of sodium, which is 109. You've got the first ionization energy of sodium, which is 494. And then you've got the electron affinity of chlorine, which is minus 364. What you're trying to work out is this. And to work that out, we're going to have to go round to it in this direction. So always go in the same direction as the area you're trying to work out. We're trying to work out the lattice dissociation enthalpy, so going from sodium chloride to its ions. So if we're going up that way, we're going to go up first and then back down again. So we're going to have to swap the formation enthalpy arrow around to make it positive. So our delta H is going to equal 411 plus 242 plus 109 plus 494 minus 364, and that equals and gives us our answer of 892 kilojoules per mole. So another example says write an equation including state symbols for a process that has an enthalpy change equal to the standard enthalpy of formation of calcium fluoride. Just writing a formation equation, so you can have calcium as a solid plus F2, which is a gas, that's fluorine in its standard state, goes to make CaF2, which would be a solid. And then it says use data from tables 1 and 2 to calculate the standard enthalpy of formation for calcium fluoride. So as I said before, enthalpy of formation using this sort of data is going to be done via a Born-Haber cycle. So we're going to make calcium fluoride, CaF2, from Ca as a solid plus F2 as a gas. And what we're going to try to get to is Ca2 plus 2F minus, going down like that. So, first atomize the fluorine. It's going to have Ca as a gas, solid, plus 2F as a gas. Then we'll atomize the calcium. So Ca as a gas plus 2F as a gas. Then we'll do first and second ionization energy of calcium. So Ca plus 2F, and then up again to make Ca2 plus 2F, and then electron affinity of fluorine to go down to 2F minus, and then a lattice enthalpy. So now we've just got to put our numbers on. So this is what we're trying to work out. So we're going to go from F2 gas to 2F gas. So that is this one here. As you can see again, the 2 fluorines already in the equation, so that's just plus 158. We then got calcium solid turning to calcium gas, that's this top one here, plus 193. We've then got calcium gas going to calcium plus, so that's this one here, plus 590. We then got calcium plus going to calcium 2 plus, that's this one here, plus 1150. And then we've got 2F going to 2F minus. Now here we've got just 1F going to F minus, so we need to multiply this one by 2. So it's minus 348 times 2, so that's going to be minus 696. And then we've got Ca2 plus 2F minus going down to CaF2. So that's the enthalpy. We've got the enthalpy of lattice dissociation for calcium fluoride. So the lattice enthalpy for calcium fluoride will be the opposite of that, so minus 2602. So that's going to be minus 2602. So to work this out, we're going to go up these and then back down again. And so our delta H is going to equal 158 plus 193 plus 590 plus 1150 take away 696 take away 2602, and that equals minus 1207 kilojoules per mole. And finally, this last couple of questions. Calcium chloride dissolves in water. After a certain amount is dissolved, a saturated solution is formed and the following equilibrium is established. There it is. It says using data from table 2, calculate the enthalpy change of this reaction. So first off, it says table 2 here. So there's no need to use table 1, so we may as well just put a big cross through there so we don't use it. And in table 2, we've got the enthalpy of lattice dissociation of calcium fluoride. We've got calcium chloride, which is what we need, which is the one in the equation. We've got enthalpy of hydration for F minus ions. Again, we don't need those. Enthalpy of hydration for Cl minus ions. We do need that. And enthalpy of hydration for Ca2 plus. Now, the enthalpy of lattice dissociation and the enthalpy of hydration both involve the ions in the gaseous form. So we can again, in this case, we're working out an enthalpy change for the enthalpy of solution. We can just use a bog standard Hess cycle. So we've got Ca2 plus 2Cl minus as gases, and the arrow going up to the solid CaCl2 is going to be your lattice enthalpy, and your arrows going up to the Ca2 plus and the 2Cl minus is going to be your enthalpy of hydration. So lattice dissociation for calcium chloride is plus 2237. May as well put the arrow around in the first place, and that's 2237. Dissociation going from CaCl2 to Ca2 plus and 2Cl minus. Then the hydration for Ca2 plus is minus 1650. And the hydration for 1Cl minus ion is minus 364. So two of them is 2 times that. So that's going to be minus 728. And then just add those together to get your delta H. So delta H equals 2237 minus 1650 minus 728. So that equals minus 141. So that delta H value is for the forward direction of that equilibrium, which is important for this next question. So it says predict whether raising the temperature will increase, decrease, or have no effect on the amount of solid calcium chloride that can dissolve in a fixed mass of water. Explain your prediction. So if we increase the temperature, this equilibrium is going to shift to the endothermic side, which, as you can see, the forward direction is exothermic, and therefore the endothermic side is the left-hand side. and that's the side where we have solid calcium chloride, not dissolved. And so this is going to decrease the amount of solid that can dissolve. And the explanation is the same sort of explanation as you would give for an equilibrium question from Chem 2. So the explanation is forward reaction is exothermic. And so equilibrium shifts left to oppose the increase in temperature.